A very good morning, class 11th and 12th. Welcome to the channel by Seema Makhijani, Chemistry Made Easy for you all. The topic for the day is the quantum model and going ahead with the quantum numbers. Now, this topic is one of the most important topics of class 11th. Your sole basis of chemistry in class 11th resides in this particular topic. Now, when had we introduced the quantum model? This was introduced when the Bohr model was rejected. And who had rejected the Bohr's model? We had two important achievements done in those days after the Bohr's model. The first was de Broglie's relation, which said that electron has a wave nature. Since electron has a wave nature, which was not taken into the account by Bohr, so this model was ruled out. The second important blow to the Bohr's model was the Heisenberg's uncertainty principle, which said that electron is not to be found in orbits, it is to be found in something called as orbitals. Now, what are orbitals? Orbitals are three-dimensional regions around nucleus where probability of finding electron is maximum. Mind you, 100% अभी भी नहीं बोल रहे. The probability of finding the electron is maximum in certain regions, and they are 3D dimensional in shapes. They have different shapes, are called as orbitals. Was the idea inferred upon after the Heisenberg's uncertainty principle was incorporated, which said that you are not 100% sure about the position and the momentum of the electron, which is your uncertainty principle. In case you have doubts in these two, both these topics are there on the channel playlist for chapter 2 structure of atom. You can have a look at these two topics with the numericals. Now, moving to the quantum model. Now, if I relate the quantum model to the address of a person, if I need to locate a person, what do I require? I require the country in which that person resides. After the country, you need the city. Only country will not help. So, if the person is in India, then you require the city. Let's say Delhi. Now, in India, in New Delhi, this person resides, and then you require a locality. Let's say the locality is Pitampura. So, India, New Delhi, Pitampura, and then you require a house number, which could be QU48. So, you require at least 4 parameters if you want to locate a person. Merely saying that the person lives in India will not help. This is exactly the difference between the quantum model and the Bohr model. According to the Bohr model, the person lives in India, that's it, which is correct, which is not wrong. But according to the quantum model, you have the further split up of the identity of the person, exactly what we do in the electron. According to Bohr, electron is in a shell, whereas according to quantum model, inside the shell you have subshells, inside the subshells you have orbitals, inside the orbitals you have electrons, two which you have to identify. So, coming to the quantum model, this is how the quantum model has been inferred upon. This quantum model helps you to find out the address of an electron in an atom. According to the quantum model, the first thing that you need to find out is the shell or the orbit to which the electron belongs. Now, if you remember, the shell or the orbit are the same, the K, L, M, N as given by Bohr. Fine. After the shell, there are many subshells in the shell, which is the conclusion by the quantum model. So, inside the shell, you have many subshells. Like in a country, you have many cities. Similarly, inside the shell, you have many subshells, and you have to locate your electron in one of the subshells. The subshells are named as small s, p, d, f, g, h, and so on. Coming after the subshell. Now, what exactly is inside the subshell? In a subshell, you have different types of orbitals. That is, there are orbitals inside a subshell. So if you come across a subshell, and there are rules for it, which we would be doing after this. In an S subshell, you would only have one orbital. In a P subshell, you have 3 orbitals. In a D subshell, you have 5 orbitals. In an F subshell, you have 7 orbitals. In a G subshell, you would have 9 orbitals and so on. How do I get these numbers is what we would be doing in today's class when we come to the quantum numbers. So the quantum model gives us quantum numbers which help us to locate an electron from the shell to the subshell, from the subshell to the orbital, from the orbital to the electrons. Inside each orbital, now orbitals are 3-dimensional in shape, and inside each orbital you have only 2 electrons. One electron is spinning clockwise, the other electron is spinning anti-clockwise. So these 2 electrons differ in spin. Fine. This is the outline of the quantum model. I would now be moving ahead into the depth of the quantum model. Moving on with the quantum numbers, there are 4 quantum numbers in all, and these are the parameters which helps you to locate the electron in an atom. So, once you reach the quantum numbers are 4 in all, and they would help you to reach the electron. Ultimately, these help you to come to the orbital. Once you decide about the orbital, then only can you locate the electrons. Fine. So quantum numbers in all are 4. The first quantum number is called as the principal quantum number. Now this principal quantum number is only for the size of the orbital. The second quantum number is called as the azimuthal quantum number. There are others names to it also. This quantum number helps you to find out the shape of the orbital. Coming to the third quantum number. The third quantum number is the magnetic quantum number. Now this magnetic quantum number tells you about the orientation of orbital in space. Now why orientation of orbital in space? The reason is that orbitals are 3-dimensional in shape. So you need to know whether it is in the x-axis, the y-axis, the z-axis, or is it in xy both, so on and so forth. So these are the possible options of orientation in space that we would be going ahead with. Coming to the last quantum number, which is called as the spin quantum number. This tells you about the spin of electron. Now when we talk about spin of electron, there are only 2 possibilities. Either it would be clockwise or it is going to be anti-clockwise. So the spin quantum number has got only 2 possible options, clockwise as well as anti-clockwise. Fine? Alright, now we would be taking up each quantum number in detail. The first quantum number is the principal quantum number, and it is represented by an alphabet small n. Now this n is the same as the Bohr. If you remember, Bohr had the shells KLMN, and he had also given that the maximum electrons in a shell is equal to 2n square. If you remember that, this is true even today. This is not wrong. That is the reason you still do it up to class 10th. So the concept, the final concept of Bohr is still true, but we have finer details of the model which were taken up by the quantum model. Fine. So principal quantum number is given by the small n, and it refers to the number of shell to which the electron belongs. Now what could be the possible values of n? Shell cannot begin with a 0. So the possible values of n are from 1. They cannot start from 0. 1, 2, 3, 4, and it can continue till infinity. Of course, this shell concept has been ruled out, but we do begin with this shell and then move on to the subshell, etc. Now this n value, if is 1, we say it is the K shell, 2 L, M shell, N shell, and so on, which means n can have any values. We also mean if the shell numbers are increasing, then definitely the size is also increasing. So your value of n is directly proportional to the size of the atom. Larger the value of n, larger would be the size of the atom, which you very well know. There was a formula done. Radius of the shell is given by 52.9 n square by z picometer, which clearly gives you this is your same principal quantum number, that is the number of shell. So this also helps you in deciding the radius of the shell. Secondly, it also tells you about the energy of the electron in a particular shell is given by the formula 2.18 into 10 to the power minus 18 z square by n square joules per atom. This formula also we did in the Bohr's model, and in this formula also this is again your principal quantum number. So your principal quantum number helps you to give you the number of shell, the possible values are up to infinity. It is also giving you the size of the atom, larger the value, bigger the size, helps you decide the radius, also the energy of the electron in a particular shell. Coming to the second quantum number, which is known as the angular momentum quantum number. At times you would also find it is called as the subsidiary quantum number and also the azimuthal quantum number. Whatever it is represented by alphabet small l, and this is referring to the subshell to which the electron belongs and the shape of the subshell. So your azimuthal quantum number is given the credit for which type of subshell does the electron belong to and what is the shape of the subshell. Now coming to the values possible, the values permitted to the azimuthal quantum number depend on principal quantum number, which means the values are, they begin from 0, 1, 2 and then their whole number values, and they go up to n minus 1, which means the values of L are dependent on the principal quantum number. For example, if your n value is 5, therefore what will be the L values? The L values can be 0, 1, 2, 3 and 4, not beyond that. Fine. Similarly, if for example your n value is 2, so the L value can only be 0 and 1, only 2 values, because it can be maximum up to n minus 1. Okay, so if the value of L is known to you, you would also know which subshell, and the shape of the subshell would also be known to you. We do not have the detailing of the shapes in our syllabus, but we must know the conclusions from the values of L. So as you know, the values of L can begin from 0, it could be 1, it could be 2, it could be 3, it could be 4, it could be 5 and so on. Fine. But till now we have only required these values up to 3. We have not required these two as yet. Fine. The name of the subshell for 0, when the L value is 0, it is said to be the S subshell. L value is 1, it is the P subshell, small alphabets. When the L value is 2, we call it the D subshell. When the L value is 3, we call it the F subshell. If at all, in the times to come, we might have more elements discovered, we might have more electrons, then in that case, we would have further subshells which could be G, H, I, so on. Fine. But as of now, we have not required beyond this point. Fine. Now coming to the shapes of these subshells. The shape of an S subshell is spherical, because the angular momentum value is 0. That means it is not oriented towards any direction. That is why the shape is spherical. Coming to the P subshell, the P subshell is found to have a dumbbell shape. Now this dumbbell could be along x-axis, y-axis, z-axis. This we would do when we do the next quantum number. Coming to the D subshell, the D subshell is a double dumbbell which looks like this. As far as the F subshell is confirmed, it is actually a triple dumbbell in shape, but we do not do in any details. We do not draw its shape because it's not possible for us on a sheet of paper in two-dimensional to draw the orbitals of triple dumbbell. So you are never even asked to do them. Therefore, if you have, let's say, n is equal to 4. Now, in that case, what are the possible values of L? L can be 0, 1, 2 and 3. If L is 0, 1, 2, 3, what will be the names of the subshell? S, P, D and F. Now, all these S, P, D, F actually belong to the fourth shell. These subshell are a part of the fourth shell, so they are named as 4S, 4P, 4D and 4F, because these subshells S, P, D, F are a part of the shell. Which shell? The fourth shell. So, this is how we name the subshells. So, when I say it is 4F, if you are given a value as 4F, you already know that this 4 is for n is equal to 4, giving you the shell number is 4, whereas if it is given F, then you also know that the L value is 3. Fine. So, by looking at the name of the subshell, you know the values of n as well as L. I will do one more. If you have a 4p, what does this conclude? N is equal to 4 and p is for L is equal to 1. Fine. Alright. With this we come to the third quantum number, which is known as the magnetic quantum number. Now, this magnetic quantum number tells us about the possible orientation, because it is a three-dimensional orbital. So, the possible orientation of the orbital in space is the role of the magnetic quantum number. This magnetic quantum number is represented by a small m with a subscript of an L, which also says that it depends on value of L, and you very well know L depends on n. So, once you have an n value, you would know the L value. Once you have the L value, you would know the ML value. They are linked to one another. So, it depends on the value of L. Therefore, the possible orientations or the possible values that the magnetic quantum number can have are beginning from minus L, going to 0 and going up to plus L. Now, what do I mean by this? For example, I have an L value equal to 3. Now, when L is equal to 3, I am talking about the F subshell as we did in the azimuthal quantum number. With the value of L, you know the subshell to which we are referring to. If L value is 3, it is the F subshell. Then, what are the ML values? ML values will be minus 3, minus 2, minus 1, 0, 1, 2 and 3. What are the total values? Count. These are 7 values. Therefore, it has 7 orbitals. Or else, it could also be the total number of orientations or orbitals, which is one and the same, is equal to 2L plus 1. Have a look at this. L is 3. So, 2 into L plus 1, what do you get? 7. So, you can learn it this way also. If you are asked how many orbitals, so you can directly give the number of orbitals also. For example, if I have an S subshell. Now, for an S subshell, what is the L value? 0. If it is 0, what are the ML values? Minus 0, plus 0, 0. You would only write it 0. So, how many orbitals are there? Total orbitals therefore are 1. Fine. So, the total electrons is what we will do after this. Coming to the P subshell. For the P subshell, what is the L value? 1. So, what will be the possible ML values? Minus 1, 0, plus 1. So, how many values are there? 3. So, 3 orientations, so the orbitals will be 3. Coming to the D subshell. For the D subshell, what is the L value? 2. So, what will be the ML values? Minus 2, minus 1, 0, 1 and 2. What are the total number of values? that is 2l plus 1 if you do it, or you count these values, it will come out to be 5. Coming to the last, F subshell, L is equal to 3, so the values will be minus 3, minus 2, minus 1, 0, 1, 2 and 3. The total values are 7 in this case. You can do it for the next also. I'll try it out for you people. Of course, we don't require it anymore. As of now, we are in no need of this. S, P, D, F. Let us take if you have a G subshell. In case you have a G subshell, what will be the value of L? 4. What will be the values of ML? Minus 4, minus 3, minus 2, minus 1, 0. 1, 2, 3 and 4. Count the total values comes out to be 9. Is that clear? Okay, now moving on to the last quantum number, the fourth quantum number, which is known as the spin quantum number, and it is represented by a small m with a subscript s, which also this is one of the quantum numbers which has only two possible values, because the spins can only be of two types. It could either be clockwise, positive refers to the clockwise spin of the electron, negative refers to the anti-clockwise spin of the electron. Also, at times you would find we do write these as this positive clockwise rotation is also represented as arrow upwards, and a negative rotation is also represented as arrow downwards. So, when we talk about the spin quantum number, the possible values are only 2. Fine. So, the spin quantum number can only be 2 as the possible values which have to be done. Now, actually in an orbital, maximum electrons is equal to 2, out of which one is the clockwise electron, the other is the anti-clockwise electron. Taking that as our basis, if we come back to what we did during the magnetic quantum number, in case if you have total number of orbitals is 1, then the electrons will be 2, one clockwise, one anti-clockwise. If you have a p subshell which has a total number of orbitals as 3, so the total number of electrons is going to be 6 electrons, 3 clockwise, 3 anti-clockwise. Whenever you have a d subshell, the L value is going to be 2. For 2L value, the ML values are 5 in all. So for 5 orbitals, your number of electrons is going to be 10, because each orbital can maximum have 2 electrons. Out of these 10 electrons, 5 electrons would be clockwise spinning and 5 electrons would be anti-clockwise spinning. Coming to the F subshell, when we talk about F subshell, it is the L value is 3, and when the L value is 3, the ML values possible are minus 3, minus 2, minus 1, 0, 1, 2 and 3. So there are 7 orbitals in all. So how many electrons can be accommodated? Each orbital can only take up 2 electrons. So the total number of electrons in the F subshell is going to be 14, out of which 7 electrons would be clockwise and 7 electrons would be anti-clockwise. Fine. So let us summarize what we have done in today's class. If you have the values of the quantum numbers, supposing I have the K shell, then the N value is 1. And in the N value, L values can be from 0 up to N minus 1. So if N is 1, this value can only be 0. And when it is 0, what is the subshell? S. For the S subshell, what are the possible ML values? ML values are from minus L, 0 to plus L. So there is just one value, which is only one value, that is 0. So we call this as the 1s subshell. In an orbital, there is only just a single orbital in that case. How many electrons are possible? In this case, 2 electrons. Coming to the L shell, N can have value equal to 2. When N is equal to 2, what are the possible L values? It can be 0, it can also be 1. If it is 0, it is S. If it is 1, it is P. So we can call them as 2S, 2P. In the S, what are the ML values? Only one value, that is 0. So there is just one orbital. In the P, what are the values? Minus 1, 0 and plus 1. So there are, in this case, you have only one orbital. While in a P, you would always have 3 orbitals. If I ask you for the total number of electrons here, this would have 2 electrons, this would have 6 electrons. So in the second shell, you would have a total of 8 electrons. Is that clear? Moving on to the M shell, Third shell, n is equal to 3. What are the possible L values? L can be 0, 1, 2. L can have 3 values. When L is 0, the ML values, it would be an S subshell, it could be P, it could also be a D. So we can have in the third subshell, in the third shell you have 3S, 3P and 3D. Talking about the ML values. Now the ML values can be minus L, 0 to plus L. So if the L value is 0, this value would only be 0. If it is 1, that is minus 1, 0 and plus 1. So you have 3 orbitals. 2, so it is minus 2, minus 1, 0, 1 and 2, so 5 orbitals. So 3s would have only 1 orbital always since it is an s. 3p would have 3 orbitals since it is a p. 3d would have 5 orbitals since it is a d subshell. This would have 2 electrons, this would have 6 electrons and this would have 10 electrons. The total comes out to be 18 electrons. Is that fine? Moving on to the last shell, that is the fourth shell as of now. If n is equal to 4, L can have what values? 0, 1, 2 and 3. These are the 4 values possible. So it could have an S, it could have a P, it could have a D, it could also have an F. So in the fourth shell you have 4S, 4P, 4D as well as 4F. When it is an S, the number of ML values are only 0. If it is 1, the L values can be minus L, minus 1, 0 and plus 1. For D it could be minus 2, minus 1, 0, 1 and 2. For F it could be minus 3, minus 2, minus 1, 0, 1, 2 and 3. So the total values here are 1 orbital because you have just one value. Here you would have 3 values, so 3 orbitals. You have 5 values, so 5 orbitals. You have 7 values, so 7 orbitals. The number of electrons therefore are 2 electrons, 6 electrons, 10 electrons and 14 electrons in the fourth shell. Please count them down. The total comes out to be how much? 32 electrons. Now do you realize that 2n square is still valid? First shell has how many electrons? 2 into 1 square, that's 2. Second shell has how many electrons? 2 into n square, that's 8. Third shell, 2 into n square, that's 18. Fourth shell, 2 into 16, that is 32. So Bohr's outline model was not wrong. But quantum model gives you that you have shells, then you have subshells, then you have orbitals, and each orbital has got 2 electrons in it. Now, before I conclude the class, the agenda is now how are you going to write the electronic configuration? For example, when we used to write it, for example, I take sodium. The atomic number is 11. By the Bohr's model, this is what you used to do. 2, 8 and 1, that's it. Over. That is applicable up to class 10th. Coming to class 11th. Sodium has 11 electrons and they are to be filled into the subshells. So when we talk about orbitals, we know in the first orbital you have only one s. In the second you have 2s and then 2p. In the third you have 3s and then 3p and then so on. But this order also has a rule. So now onwards you would be filling your electrons into the orbitals rather than in the shells. This concept is ruled out because this was given by Bohr. According to quantum model, you have to now fill electrons in the orbitals or the subshells. So if I have 11 electrons and I need to fill them up, as you very well know, the first shell has only one s, second has 2s and then 2p, third has 3s, 3p and 3d and so on. So using these orbitals and subshells, we will now have to write down the electronic configuration in these subshells or the orbitals. So if I have 11 electrons, S has a maximum capacity of 2. So 2 electrons done, another 2 makes it 4 electrons. Then P has a capacity of 6, so makes it 10 electrons. You are left just with 1 electron and that is your electronic configuration now onwards for class 11th and 12th. So the thumb rule before I end the class is that you should know whenever you have an S subshell, it can have maximum 2 electrons. A P subshell will maximum have 6 electrons. A D subshell will maximum have 10 electrons and an F subshell would maximum have 14 electrons. If you know this, then writing the electronic configuration should not be difficult for you all. Fine? Now to write the electronic configuration and to go in depth, you would require three things. There are rules to write the electronic configuration, and these rules are known as the Aufbau's rule, the Hans rule, and the Pauli's exclusion principle. For all these, you already have videos on my channel. You can refer to them and then be an expert at writing the electronic configuration and the quantum model of class 11th. So, thank you kids. I hope I've tried to convince you with the quantum model and you have some grasp over the topic. Keep liking, keep sharing, be safe and stay happy. Bless you all.